All right, so welcome to Math 150 Calc 3. This is going to be lecture 5. And so what we're going to do today is we're going to start talking about vectors and the basis for multivariable calculus. So we'll talk a little bit about vectors, properties of vectors, briefly mention what the dot product is, although we've already seen that, and then talk a little bit about matrices acting on vectors at this time. We're not going to do too much with matrices acting on vectors. This is really done in linear algebra. A large number of you will continue to linear algebra, or you will take other classes, maybe econometrics, where matrices are used. So seeing a little bit of matrices now is not going to be bad. So my philosophy is I am quite happy to spend some of class time on things that you will not be tested on. If this bothers you, I am happy to, of course, add more test questions, but I think it's better to just use this as an opportunity to just see some things beforehand so that when you see them later, it's not the first pass on it. And just remember that there is a reason behind everything that is done. Sometimes that reason may be very hard to find. Who remembers their trig? Trigonometry. Okay, what is 1 over cosine? What is that called? Yeah, secant. Does that bother you? Yes, it bothers me. What should 1 over cosine be called? Cosecant. What should 1 over sine be called? Secant. So there must be a reason as to why 1 over cosine is called secant and 1 over sine is called cosecant. And there actually is a reason, and I've looked at it. I would still rather have 1 over cosine go with cosecant. I at least understand the reason behind it. But you want to think there must be a reason behind the notation. There must be a reason behind why we're doing things this way. We can define anything we want. Most of the things we define will just be useless and not worth studying. So which things are worth studying? It took a long time to come up with the right way to generalize things from one dimension. And we have the complex numbers, which is absolutely wonderful. You add the square root of -1. So where do you first see in your algebra class the square root of -1 of i's? Anybody remember where you first see the square root of -1? Or at least where you see the square root of -1 in junior high or high school? So when you're trying to solve equations, which equation do you sometimes have to use the square root of -1? So how do you solve a quadratic? What do you use?
Quadratic formula.
So it's the roots are -b plus or minus the square root of b squared minus 4ac over 2a. B squared minus 4ac could be negative. So what this means is you could start off with a polynomial with real entries, but the roots could be complex. So for example, if I give you the parabola x squared plus 1, well, x squared plus 1 is never going to be 0. What's the smallest value x squared plus 1 takes on? 1. So it has no real roots, but it does have a complex root, the square root of -1, which we call I. What is absolutely phenomenal is that once you add the square root of -1, I cannot write down any polynomial of finite degree with even complex coefficients where you can't solve it. Any polynomial degree n with complex coefficients has n roots involving something of the form x plus I square root of x plus iy. You don't need to introduce anything else. Once you introduce I to solve x squared plus 1 equals 0, you get everything else. And so people then try to generalize this. Well, is there something with 3 components? And it turns out there wasn't anything that had the same kind of nice structures as the reals and the complexes with 3 components. The next one was actually with 4 components. And with 4 components, this is called Hamilton's quaternions, you lose commutativity. So the order in which you multiply now matters. So we have something of dimension 1, dimension 2, dimension 4. Anybody want to guess what comes next? 1, 2, 4. What dimension would you guess next? 8. And these are the octonions. And in addition to losing commutativity, now you lose associativity. So A times B times C is not the same as A times B times C. So the reason I'm saying this is I really want you to think about why are we doing what we're doing? We're trying to come up with good ways to attack things. So let's start off with vectors. So it has magnitude and direction. It often has a base point. So it's where is the action happening? So I can give you a generic vector. I can give you a vector, say 2, 3. So moving over 2 units to the right and 3 units up. And I could have it based over here at the point 0, 0. So it's often very convenient to talk about where is the vector based. I'm drawing a vector based at this point. And if I give you 2 vectors, if I give you v equals, say, 2, 3, and w equals 4, -2, what would v plus w be? 6, 1. And so the way we add vectors is, first here would be v, and then w, I would go something like that. So here would be v, here would be w, and then this would be v plus w. Why am I putting the arrows over v and w? Yeah, to denote that they're vectors, so that I can quickly look down and see that this is a vector. I don't need to do this. A lot of books use bold type, but when I'm writing on the board, or I think we still say board, even though it's something like this, I'm not going to keep pushing down hard and making things bold. I just write a vector. It's nice to have notation that you can just quickly glance on and see what's going on. So a vector has magnitude and direction. So what is the size of a vector? So the standard vector to give you is, here's the vector 3, 4. So why am I doing this? This is the standard Pythagorean formula. So what this is saying is, I move over 3 units, I move up 4 units, and so the hypotenuse is 5. So I can figure out the magnitude of the vector. So I like to write double absolute value signs. V is the length of V. A lot of times people just overload the absolute value and say, look, initially we defined the absolute value to be the absolute value of a real number. Then maybe we extended it, we allowed ourselves to take the absolute value of a complex number. Now let's allow us to take the absolute value of a vector. And we're just going to always use just 2 parallel lines, one on the left, one on the right, to just note the magnitude of whatever the hell is inside. Right? So we could use, that's fine. It's just what notations you want to use. I like to use parentheses for my vectors. Some people use angular brackets. Doesn't really matter. And the question is, do you want to write your vectors as columns or as, columns or rows? Which would you rather write things as, a column or a row? Why? So one is the natural flow, but why not just going from top down? We could write V equals 3, 4, 5, 6, or we could instead do V equals 3, 4, 5, 6, but notice what happens to the text. If I have a big vector like that, it's going to change how things are displayed. And look at all that blank space. Again, 21st century, blank space is not quite as bad as it used to be, but it was a real challenge for centuries in terms of how do you actually write math text or text in general? How do you insert images? And a lot of times when you're doing these block printings, and we actually have some of these old books in the rare books collection here if anybody's interested, the way they did old Euclid books on geometry is they would often have just the images on the side where you would just have to take like an entire part of it because you didn't want to interrupt things, or it would be just a perfect square. And so There is reason behind doing things. I like to write them as a row vector. It doesn't really destroy what's going on around it. All right, so once you have objects, the next thing you can ask is, what can I do to it? And this should not be in the mindset of, you have pledges to a fraternity or sorority, or what can we do to our pledge? What reasonable things might you want to do to vectors? So given vectors, we could do what? One of them was we could add and subtract. What else could we do? So I can add two vectors. And again, given two vectors, they have to have the same number of components. So maybe V and W live in Rn, then V plus W is in Rn. And what Rn is tuples of n real numbers. So it's the set of all points x1 through xn, each xk is a real number. There are other vector spaces we can look at. We don't have to look at vector spaces just of n tuples of numbers, but for now, that's what we're going to do. So I could add two vectors. What else could we do? By what? By what?
By each other.
Okay, so the question is, can we multiply and divide vectors? Can we multiply and divide? It's a natural thing to ask. We can multiply and divide numbers. Can we multiply and divide vectors? In general, the answer is we definitely cannot divide. We don't really know what does it mean to take a vector and divide by a vector. But there are two types of multiplications. There's the dot product. V dot W is V1 W1 plus Vn Wn. Or in more concise notation, the sum k goes from 1 to n of Vk Wk. And so we start with vectors in Rn, we get a real number. And it turns out that that real number has a lot of significance. It tells a huge story. There is also the cross product. I don't think the lecture covered the cross product. Is that correct? Right. So we will see the cross product sometimes exists. And it's another way to combine two vectors. And this is a vector. So there is a way to multiply special vectors and get a vector out, but not always. Every now and then, things just work out nicely. And three-dimensional space, it turns out, works very, very nicely, that if you have two three-dimensional vectors, you can take their cross product and get another three-dimensional vector. This doesn't work in general. It's a very nice feature of living in what looks like a three-dimensional spatial universe. There is one other simple process we can do. A vector has magnitude and length. We talked about combining two vectors. You could also rescale. So A times V would just be AV1, AV2, AVN. So we can, given a vector, we can rescale it. Okay. So these are some of the basic properties of things you can do with vectors. We talked a moment ago about what is the length of a vector. And what we did is we proved essentially the length of the vector using Pythagoras in 2 dimensions. But what if I give you something in 3 dimensions? Or 4, or 5, or 6. The more dimensions I have, the harder it is to just visualize what's going on. How many points determine a line? 2. How many points determine a parabola? So parabola has 3 unknown coefficients, ax squared plus bx plus c. A line has 2 unknown, ax plus b. 2 points Give me two equations to find A and B. For parabola, how many points would I need? 3. For quartic, how many would I need? For quartic, 5. Parabola was 3. I skipped cubic. I jumped up to quartic. Right? So quartic has 5 coefficients. The fourth, third, second, first powers, and then the 0th power. So if I give you polynomials of given degrees, if you give me enough points, I can figure out what they are. What if I want to try to figure out the length of a vector in, say, 5-dimensional space? No, that's hard. What if I could figure out the length of maybe 4-dimensional space and then maybe bump up to 5? Okay, if I want to get 4 dimensions, which I did before I do 4 dimensions? 3 dimensions. And before I do 3 dimensions, 2 dimensions. Before 2 dimensions, 1 dimension. Okay, well, 1 dimension, pretty easy to go because there's only one direction my vector is going to reach. See, how far is it? So lengths of vectors. Lengths of vectors. 1-dimensional space. Well, it's just that. Our vector v is just going to be some number. In 2 dimensions, what do we use? So how do we find the length in 2 dimensions? Pythagoras. So now, for 3 dimensions, we know the length of a vector in 2-dimensional space. So what I want to do, and this is where I have almost no chance in hell of drawing this well. And so I will just, I have some vector coming out like this. And I try to write it as something in maybe the XY plane and something coming up. So this is where it's maybe nice to be able to just show things using the screen. Oh, good. I'm finally going to get to use chalk again. So I have my vector over here, and I can just look at it. How much is coming out, say, in the XY plane, and then similarly, how high up is it coming like that? So I've put this vector, this 3-dimensional vector, into a 2-dimensional plane. I've got the z component coming up, and I've got a component in the XY dimension. So what I can do is and so what I can do is I've got my vector v, I'll write it as xyz. I'll write v as xy0 plus 0, 0, z. And so I'll write v as, say, v1 plus v2. And then the length of v squared is the length of v1 squared plus the length of v2 squared. What's the length of v2? The vector 0, 0, z. What's its length squared? Z squared. And so this is going to be the length of v1 squared plus z squared. But v1 is really just living in the plane. And by Pythagoras, we know that that's just x squared plus y squared. And so now we know that if a vector has 3 components, its length is going to just be the sum of the squares of the components and then take the square root. So this was the 3-dimensional proof. What we should technically do now is we should rigorously prove by induction that this holds for n dimensions. Or we can just wave our hands. I prefer to just wave hands and say, look, we did it like this. If we had 4 components, what we would do is we would have w, x, y, z. We would first pull off the z, and then we'd be left with w, x, y. And by induction, we know that that's w squared plus y, x squared plus y squared. So really, once we handle the 2-dimensional case, we get all the other cases without any trouble. It just propagates up very, very nicely. So we're left with the length of v is the square root of v1 squared plus dot 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 plus vn squared. And so now we have our formula for that. Any questions about the lengths of vectors, adding vectors? How many of you have done physics? So if you've done physics, you've hopefully seen some force diagrams. Maybe you have gravity acting down, maybe you have a force of friction, and you have your force vectors, showing what's happening to the object. Okay. As always, if there are specific things that people want me to cover in the lecture, either let me know in class or just by raising your hand or email me beforehand, and I'm happy to put that in. If not, I will just adjust and just talk about things that I think are worth highlighting from the lecture or connections. Okay. How many different ways do you know to write down the equation of a line in the plane? So formulas for the equation of a line in a plane. How many different ways do we know to write down the equation of a line in a plane? I can think of 3. Anybody remember any formulas for equation? Yes. Okay, so mx plus b. What is mx plus b? That's called. It might be standard slope intercept. You might be right with standard. I'm just not sure. It's been so long since I've done this. There are a lot of things that have definitions and names that most of us sadly do not remember. How many of you have ever seen a fraction like 1/3? What's the numerator? What? Denominator? What's the line between them called? There is a name for that. So I'll leave that for you to Google or search. There is a name for something like that. It really doesn't seem to have impacted your ability to work with fractions, not knowing the name for the line dividing. Okay. But it does have a name so that you can refer to it. It might be that this is the standard form because we try to always write things in the form y equals mx plus b. So that's one. What's another one? Point slope. So y minus y1 equals mx minus x1. Wait a minute. Yeah, yes, this is point slope. And so here we're given m and b. Here we're given x1, y1, and m. And there's one other version. The last one is point. Is y minus y1 equals y2 minus y1 over x2 minus x1, x minus x1. So this is point. We're given x1, y1, and x2, y2. I really never use point. If I'm given point, I first calculate the slope, and then I use point slope. And so if we're trying to think of what's going on with a line, so maybe here's my line, here's my point x1, y1. And then I go over 1 unit and I go up m units. And once I have that slope, I know the line. So long as I know the base point, as long as I know any point on the line, I can now get every other point. So if I wanted you to write down the slope, how would you write the slope? So for this line, what would the slope be? So I move 1 unit over in x, I move up m units in y. What would the slope for this line be? It would just be m. Now let's think, is this going to generalize well for multivariable calculus? I will occasionally remind you that we are actually in a multivariable calculus class, even though it will be a while before we actually differentiate or integrate. We're spending time learning notation. If you guys had learned things like, what was the name of that line between the numerator and denominator, we wouldn't have to spend all this time now reviewing things that you should already know. But I can't trust you on anything. So we've got to go through all this stuff. So this is the slope. We want to generalize this to higher dimensions. What do you think the slope should be for a line in 3 dimensions? Do you think it should just be one number? See, in 2 dimensions, if I walk in the x direction, I then go up a certain amount in the y direction. But in 3 dimensions, when I have a line, I have more ways to walk. I can walk in the xy plane, and then only certain walks then do I go up and hit the new point on it.
Would it be an equation?
What do you mean by an equation?
Like a one-dimensional equation?
Not quite. So the question is, yes. So maybe the slope is a vector. So maybe as we go higher and higher up, the slope should be vector. So maybe this should be written as a vector. So how could we vectorize this? That is a word. You don't need to Google me, you can just trust me. How would we vectorize this? We could, of course, consider this as a one-dimensional vector as m, but I claim there might be a better vector to associate to this.
0m.
Not 0m, but you're close. 1m. Why? We move over 1 unit, and then we move up m units. So what we're going to do is we're going to try to redo, this is either algebra 1 or algebra 2, from the point of view of vector analysis. And then this will generalize much better when we get to multivariable calculus. So why do we care so much about this? Well, in Calc 1, we saw, and we did this with Newton's method, how powerful the concept of a straight line is. We take a complicated function and we replace it with a straight line. We understand straight lines. So if I give you something complicated and I can replace it with a straight line, this is progress. So what we want to do is we want to take this in such a way that it's going to generalize nicely to several variables. And so the idea was, instead of writing the slope as just a number m, let's write it as a vector 1, m. And so now let's try to think, how would we vectorize a line in the plane? So we have a point, I'll call it maybe v0 is, x0, y0. And we have a slope, which is 1, m. And we have the equation, y equals m x minus x1 plus y. And this is our equation. Or y minus y1 is m x minus x1. So what we want to do is we want to write it in terms of a vector. So I have some vector xy, and I want to write it in terms of our initial point, x0, y0, or sorry, I should be using x0 and y0. And so where am I at some later time? I want to do it as some kind of function of where we started. So what do you think should go into that other parenthesis? Yeah, 1 and m. And maybe what we'll do is we'll put in some t over here, some time. And so we get, x of t, y of t is going to be t times our slope vector 1m plus x0, y0. So x of t is x0 plus t, y of t is y0 plus mt. Okay, when I write it like that, that really makes sense. And here what we're doing is we're parametrizing the line. this makes sense. The line is a one-dimensional object. Once you tell me how much time has elapsed from the start, I should be able to tell you precisely where I am. And so I start at x naught, y naught. So when t equals 0, we can call this v of t. When t equals 0, v of 0 is just the initial point x naught, y naught. So we start at x naught, y naught, and as time grows, we just move. Who knows what WLOG stands for? Anybody heard the phrase WLOG? Without loss of generality. So basically it says it doesn't really harm anything if we just assume we have something of this form. So a lot of times I might as well assume that my leading coefficient is positive. If it was negative, I multiply through by -1. And so without loss of generality, it suffices to study the case when the leading term is positive. When you look at this vector 1m, this has a really special form. The first component is 1. Could we have the first component be 2? So let's consider x of t, y of t equals, say, x naught, y naught plus your t times 1m. And let's consider something new. X tilde of u, y tilde of u is x naught, y naught. So they have the same base point plus u times 2m. Do these give me the same line in space? Or do they give me different lines in space? What do you think? So if I have a point on the first, if there's a value of t, is there a corresponding value of u? And conversely, if I have something on the second, is there a t that corresponds to that u? So what do you think?
Yeah.
Okay, so what would be the relation between t and u? So u equals 2t, or t equals 2u. Sorry, u over 2. So if t equals 4, did we get this right? No, I think it's the other way. I think you want t to be equal to 2u. You'd pull up the 2, right? So we want t to equal 2u, or u equals 2t. I'm sorry, equals t over 2. So we could write this one as x naught, y naught plus 2u, 1m. I just pull out the 2 from the vector. And we see that t corresponds to t2u. So they really traverse the same curve in space. Which one do you think is moving faster? If I increase t by 1, when I increase u by 1, which one do you think is going to travel faster? So which has the greatest chance? So if t increases by 1, I move by the vector 1m. If I increase u by 1, I move by the vector 2m. So which one would have a greater movement for the same change? 1 unit of t change or 1 unit of u change? 1 unit of u change would have a greater. And so we really want to be careful in something like this. We don't want to confuse ourselves. It's very convenient to just adjust things so that the x component is 1. So one normalization the x component is 1. There is another normalization. Another is the norm of the slope vector equals what? What would be a good norm? What would be a good length for it to have? 1. So it's a vector of unit length, and then we just specify some direction. These are the two most natural normalizations. One of these normalizations is better than the other. Which normalization is better? So if I give you a vector, can you always rescale it so that the x coordinate is 1? Can any vector be rescaled so that the x coordinate is 1? Well, I could rescale it by a negative number. It's okay. There's one thing you have to be careful with. If I give you the vector 3, 7, I can rescale by 1/3. If I give you the vector negative 3, 7, I can rescale by negative 1/3. What do you have to worry about? If x is 0. No. What if the x coordinate is 0? What would it mean for the x coordinate to be 0? What would the slope be? So what would be the slope if the x coordinate is 0? So I don't move anything, and the change in y is a finite amount. Yes. Undefined. What kind of line would it be in the plane? It would just be a vertical line. So we lose the vertical lines when we divide it like this. So you have to be careful when you're doing something like this, that we might miss the vertical lines. So we lose vertical line. Anybody know what 0 times infinity is? The answer depends. For example, I could take the limit as x goes to 0 of x times 1 over x cubed. As x goes to 0, this looks like 0 times infinity. And what would that be in this case? Yes, it would be infinity. But if I gave you the limit as x goes to 0 of x cubed times 1 over x, it also looks like 0 times infinity. What would that be? 0. And if I give you the limit as x goes to 0 of 17x times 1 over x, looks like 0 times infinity is 17. So when you have certain products, they're not defined. 0 times infinity, you have to do it through a limit process. What I'm going to do now is I'm going to show 0 times infinity can be negative 1. Okay? And I need to recall some results that you've hopefully seen before. So imagine I have 2 perpendicular lines, and this has slope m1, this has m2. Does anybody remember what the product of the slopes of 2 perpendicular lines is? So the result, yes, it's negative 1. As a hint, given that I'm trying to show something is negative 1, if you had to just take a guess, negative 1 is not a bad thing to guess. Of course, early in the class, I deliberately skipped the quartic and went to the quintic, so you do have to be a little bit careful. It's early in the semester, you don't know exactly how I phrase things. So the product of two slopes is -1. I'll quickly sketch that in a moment. Why is this interesting for us? Well, if I take the special case of the vertical line and the horizontal line, what is the slope of the horizontal line and the vertical line? So if you look, stop the share for a moment. So if you take two lines like this, the product of their slopes is -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, undefined, -1, -1, -1, -1, -1, -1, -1, undefined, -1, -1, -1, -1. It seems reasonable to say, well, it's -1 everywhere except for these places where it's undefined. Let's just say it's -1 there as well. And this is a reason to interpret in these cases that maybe really is -1. As a quick proof, what I'm going to do is draw a really bad unit circle. Without loss of generality, I might as well assume that they intersect at the origin, right? I can always just adjust my coordinate system to have them intersect at the origin. So intersect at origin. Let's call this angle θ1. Let's call this angle θ2. This point over here is cosine θ1 sine of θ1. This point over here is cosine θ2 sine θ2. And this gives me a chance to just review some trick. I have a point on the unit circle. So what's the slope? So M1 is just going to be sine θ1 over cosine θ1. M2 is sine θ2 over cosine θ2. But what do we know about θ2? What is θ2? Yeah, θ1 plus 90. I'm going to write pi halves to just get us in the habit of using radians, but either one is fine. And now we use our angle addition formulas. So the numerator is going to be sine θ1 cosine pi halves. What's the cosine of pi halves? So it's sine θ1 cosine pi halves plus cosine θ1 sine of pi halves. Down below, it's going to be cosine θ1 cosine pi halves minus sine θ1 sine of pi halves. The cosine of pi halves is 0 because we're all the way here at the top. And the sine of pi halves is 1. So for the numerator, the cosine of pi halves vanishes. So this term is just going to be sine pi halves is 1 is just cosine θ1. And then down below, cosine of pi halves is 0, so this term vanishes. Sine of pi halves is 1, so we get negative sine of θ1. Oh, well, that's just -1 over m1. And there's the product of the slopes is -1. So we've proven that the product of the slopes is -1. So we have many ways of writing equations of lines. We had 3 different ways here. If we want to find the way that generalizes best to higher dimensions, we actually have to revisit how we did this. And rather than just writing the slope as a number m, we should really view the slope as a vector, 1, comma m. And when we do that, now we have an idea of how to generalize. So we then said, hey, we can write a line as x of t, y of t is t times 1m plus the base point. Well, what if we wanted to do a line in 3-dimensional space? So we would have x of t, y of t, z of t. would be my base point, say x0, y0, t0. Oh, not t0, sorry. 0 plus t times what? Times my slope vector. And I'm not going to invite it now as, I could maybe try to write it as 1yz, but I don't know that the first component is non-zero. So the best is to just write it as maybe m1, m2, m3. So we could write it as, v at some time t is the initial point plus t times the slope vector. And this is a very natural way to generalize the equation of a line. And then depending on how you want to write things, you might use different notations. You might use v for the slope vector. Maybe use, p for point and v for slope vector. So we might write maybe p at some time t is the initial value plus t times the slope vector. The worst notation I've ever seen in my life I saw this in a physics textbook, P equals M. Anybody know what equation this is? When either Stephen Hawking or one of the people like that was writing a popular book on physics, they were told for every equation you lose half your audience. And there were two equations that they said, I don't care if I lose, 3 out of 4 people, I have to put these two equations. These are two of the most famous equations in physics. Anybody want to guess? Big famous physics equations. So 1 is equals mc squared. Well, we don't have anything squared, so it's not that, it's the other one. This is F equals ma, where P stands for force and F stands for acceleration. Is it wrong to use this notation? No. It sure hell is not useful. You're going to confuse people. Really spend the time and think, what do you want to choose for your names? Do I want to use maybe P for points? When I look down, I keep seeing P for point. This is why we use a prime for derivative and a capital letter for the antiderivative, so that when we quickly look down, we can see how things are going. So these are one-dimensional objects. After studying a line, what might we study? What might you do after a line? You might study a plane. So, this is advanced, so P of t would be the initial point plus t of a vector. Anybody want to guess? Now, for a plane, how many free dimensions do I need? How many free variables? How many dimensions is a plane? 2. All right, so a line is 1, so I should probably have 2 inputs. I have my initial point, and anybody want to guess what comes next? So this is your chance to just conjecture. Maybe a plane is going to be of the following form. What do you know lives inside a plane that we've already studied? So if I give you a plane, what must be living inside this plane? What kind of objects? Line. So we know we have to have lines inside of it. So it should start off with maybe t and some direction v1. What else might you want to put in? Yeah, plus SV2 is that I choose 2 different directions. I choose a base point, and then I can go any distance among the first and then any distance among the second, and that will give me my plane. And that'll give me a nice two-dimensional object to walk along. So we'll talk about planes later, but you can see the power of our notation. Once we had the equation for a line, to generalize to a plane wasn't that bad. All right, so I'm going to stop here. If this was your first real lecture based on watching the videos and coming to class, if this worked well for you, that is terrific. If it did not work well for you, then please send me more details of what you want me to talk about from the lectures. I want to really try to use class time effectively. And if you're understanding the lectures of the book, then I can use this to really drive home the material.